Before we start our e-learning module, before we are starting on the topic on alkane, please familiarize with the 4 learning objectives for this topic. These are the learning outline for the topic on alkane. Before we go into the chemistry of alkanes, we must understand what alkanes actually are. Alkanes are actually saturated hydrocarbons that can exist as branch chains, straight chains, or in rings. The general formula of alkanes is CnH2n plus 2. So, what does the word saturated means? Okay, the word saturated actually means that alkanes contains only C≡C and C≡H bonds. Next, we're going to understand how alkanes are actually named. In the alkane family, each member of the straight chain alkane is given the suffix ane. I'm sure you have learned that CH4 is known as methane. The second member, C2H6, is actually known as ethane. And the third member, C3H8, is known as propane. From C4 alkanes to C10 alkanes, the names of the alkanes are butane, pentane, hexane, heptane, octane, nonane, and decane. In organic chemistry, we can have different formulas to represent organic structures. For example, chemical formula, displayed formula, structural formula, and skeletal formula. Next, we are going to watch a clip on how to interpret skeletal formula in organic chemistry.
Abbreviated structural formulae for alkanes are called line angle drawings. Chemists use abbreviated line angle drawings for organic molecules in everyday work. Each line represents a carbon-carbon single bond, and the vertex of each angle represents a carbon atom. Hydrogen atoms do not appear in the formula. Examples shown are the line angle structures of pentane, hexane, and heptane. Abbreviated structural formulae for alkanes.
When we try to represent straight chain alkanes with displayed formula, we find that the carbon atoms are actually in line with one another, forming a straight line. But in actual fact, are straight chain alkanes really straight? Please find out for yourself from this video.
When we put 2 carbons together and make an ethane molecule, the hydrogen-carbon-hydrogen angles and the hydrogen-carbon-carbon angles are all around 109 degrees. This happens because the orbitals of an sp3 hybridized carbon are pointing towards the corners of a tetrahedron. We're going somewhere with this.
If we add another carbon to our ethane chain, we get propane. Check out how the carbons are arranged in relation to one another. The 3 carbons here that make up the propane molecule aren't in a straight line. Instead, the 3 carbons are in a carbon-carbon-carbon bond, and that bond has an angle of about 109 degrees. When carbon starts to form long alkane chains, they aren't in long straight lines, as some drawings would have you to believe. The carbons are actually in a sort of zigzag, so they can all have that 109-degree carbon-carbon-carbon bond angle.
When one or more hydrogen atoms of a straight chain alkane are replaced with alkyl groups, we will get branch chain alkanes. For example, 2 of the hydrogen in butane can be replaced by 2 alkyl groups to form 2,3-dimethylbutane. Alkyl groups are named by replacing A and E with YL. The general formula for alkyl group is CnH2n plus 1. The first member of the alkyl group is CH3, known as methyl. The second member, C2H5, is known as ethyl, followed by C3H7, which is also known as propyl. Next, we are going to watch a short clip on the alkyl groups.
We can consider an alkyl group as being the group of atoms remaining after removing one hydrogen from the molecule of an alkane. Alkyl groups do not exist independently, because in actual molecules, the missing hydrogen atom is replaced by another atom, such as carbon, oxygen, nitrogen, and others. To name the simplest alkyl group, where the potential point of attachment is at the end of the carbon chain, we take the IUPAC name of the corresponding straight chain alkane and replace the ending -ane by the ending -ile. Methyl, ethyl, or butyl groups are examples of simple alkyl groups. We can
To name an alkane, there are generally several steps and guidelines that we must follow. Please remember that, although the general guidelines are the same, for different teaching resources, the steps to name an alkane may be different. However, the first step of naming alkane is always to identify the longest continuous chain of carbon, which is also known as the parent chain. Next, we are going to watch a video clip on how to name an alkane properly.
Alkanes with 4 or more carbon atoms can form branched structures and structural isomers. Naming them is more complicated. To name structural isomers, we apply 4 rules in the following order. First rule: identify and name the longest straight carbon chain. Second rule: add the names of any substituents as a prefix in alphabetical order. Third rule: use replicating prefixes di, tri, tetra, etc. if there is more than one identical substituent attached to the main chain. Do not alphabetize the prefixes di, tri, tetra, etc. Fourth rule: number the chain from the end nearest to a substituent and identify the carbon to which the substituent is attached. Alkanes with 4 or more carbon atoms can form branched structures and structural isomers. Naming them is more complicated. To name structural isomers, we apply 4 rules in the following order. First rule: identify and name the longest straight carbon chain. Second rule: add the names of any substituents as a prefix in alphabetical order. Third rule: use replicating prefixes di, tri, tetra, etc. if there is more than one identical substituent attached to the main chain. Do not alphabetize the prefixes di, tri, tetra, etc. Fourth rule: number the chain from the end nearest to a substituent and identify the carbon to which the substituent is attached. Alkanes with 4 or more carbon atoms.
Now that we have learned how to name an alkane, let's go through the first example on page 6 of your lecture notes. Remember, what is the first step to name an alkane? It is to identify the longest chain of carbon atom. In this example, the longest carbon chain is a 5-carbon chain. Hence, the parent chain is known as pentane. Next, we need to identify the substituents attached to the parent chain. In this example, we find that there is a methyl substituent. However, at what position is this methyl substituent attached to the parent chain? This is when we need to number the carbon on the parent chain. We can number the carbon on the parent chain from left to right or from right to left. But since the guideline tells us that a lower numbering is preferred, the methyl group is attached to the carbon 2 of the parent chain. Therefore, the name of this alkane is 2-methylpentane instead of 4-methylpentane. For the previous example, the naming was more straightforward as there is only one substituent. How do we name an alkane that has two similar substituents? Applying the first three steps from the lecture note will help us to identify that the parent chain to be a 3-carbon chain. Hence, the parent chain is known as propane. The substituent in this alkane is the methyl group. However, there are two of them and both of them are attached to the second carbon on the parent chain. The guideline tells us that for the same alkyl group which occur more than once, we need to add prefixes like di, tri, tetra to indicate the number of groups. And since there are two methyl groups, we need to use di as the prefix. Considering all this, the name of the alkane is 2,2-dimethylpropane. Notice that to separate two numbers, a comma is used. And to separate a number and a word, a hyphen is used. Just now, in the previous example, there are two similar substituents. But what if there are three substituents and the substituents are different? We will illustrate this using example 3. Now, try to identify the parent chain yourself. If your answer is hexane, you are correct. Then, what are the substituents attached to the parent chain in this alkane? You should be able to identify that there are 1 ethyl and 2 methyl groups as the substituents. So now there's a problem. In the naming, should ethyl come first or methyl comes first? Since step 4 in the lecture notes tells us to name the substituents in alphabetical order when there are more than one substituent in the parent chain, ethyl starting with the letter E should come first, before methyl starting with the letter M. But then, there is another problem. If we follow the blue numbering, we get 3-ethyl 4,4-dimethylhexane. But if we follow the red numbering, we get 4-ethyl 3,3-dimethylhexane as the answer. So which is correct? Since step 3 tells us that a lower numbering is preferred, we should then follow the red numbering, because 4 plus 3 plus 3 gives 10, which is a lower number than 4 plus 4 plus 3, 11, if we adopt the blue numbering. Hence, the correct answer is 4-ethyl 3,3-dimethylhexane. After we have gone through 3 examples, you can now attempt example 4 yourself. When you have finished, you can click on the answer icon to check your answer.
please refer page 8 of your lecture notes. Following this example of 2-methylpentane, please attempt to draw the skeletal formula for the other 3 alkanes in the self-practice. You can also refer to the video on skeletal formula.
Abbreviated structural formulae.
In this chapter, you are going to learn how alkanes can exhibit structural isomerism. The video in the next slide will help you to understand the structural isomerism in alkanes.
The first 3 members of the homologous series of alkanes can exist only as straight chain structures, commonly named normal alkane structures. However, those with 4 or more carbon atoms are capable of forming branched structures. The simplest case is the 4th alkane, named butane, which can appear in 2 forms known as structural isomers. These 2 forms are commonly named N-butane and isobutane. The number of isomeric alkanes increases rapidly with an increasing number of carbon atoms in the molecule. However, it's difficult to predict how many isomers will appear for a compound having a particular formula. Moreover, for bigger molecules, the number of structural isomers is practically countless, and there is hardly any difference between them. The first 3 members of the homologous series of alkanes can exist only as straight chain structures.
After watching the clip, you should have a better idea of how alkane can actually form structural isomers. Structural isomers are compounds that has the same molecular formula but different structural formula. It only occurs for alkanes with more than 3 carbon atoms. Hence, the first 3 members in the alkane series have no structural isomers.
The first member in the alkane series to exhibit isomerism is butane. Butane can form 2 structural isomers, namely butane and 2-methylpropane.
Following butane is pentane. Pentane can actually form 3 structural isomers, namely pentane, 2-methylbutane, and 2,2-dimethylpropane. You might be able to guess that as the number of carbon increases for the alkane, the number of structural isomers it can form will also increase. Hexane can form even more structural isomers than pentane and butane. In fact, hexane can form up to 5 structural isomers.
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the second carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the third carbon position produces 3-methylpentane. Moving the methyl group to the fourth carbon position appears to make 4-methylpentane. But wait! Rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the second carbon position produces 2,3-dimethylbutane. Moving the methyl group to the second carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the third carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
Now, take a step back and think of this question. Do you consider 1,1,2-trimethylpropane to be the name of the following structural isomer of hexane? We have reached the first checkpoint of this e-learning module. Answer these 5 questions and see how well you have understood chapters 1, 2, and 3.
In this chapter, we will find out more about the boiling point, melting point, and the solubility of alkanes. In contrast to giant ionic and giant molecular structures, alkanes are actually simple molecular structures. They are also non-polar in nature. There is weak intermolecular van der Waals forces of attraction between the alkane molecules, which can be overcome with a low amount of energy. That is why alkanes have low melting and boiling points. As we can see from the table, as the number of carbon atoms increase in the alkane, the physical state at room temperature of the alkane moves from gases to liquids to a solid state. This can be explained by the relationship between the molecular size of the alkane and the extent of van der Waals forces of attraction. As the number of carbon atoms in the alkane increases, the molecular size of alkane also increases. This leads to greater extent of distortion of the electron cloud, which leads to more extensive van der Waals forces of attraction operating between the alkane molecules. In the end, more energy is required to overcome the van der Waals forces of attraction, leading to higher melting and boiling point. That is why melting and boiling points of alkane increases with its molecular size.
Similarly to the boiling points, the melting points of straight-chain alkanes rise with an increasing number of carbon atoms in the molecule. This happens because of the regular increase in molecular mass of the alkanes in the homologous series. Interestingly, the melting points of alkanes having an even number of carbons in the molecule increase differently from the melting points of alkanes having an odd number of carbon atoms. Similarly to the boiling points, the melting points of straight-chain alkanes rise with an increasing number of carbon atoms in the molecule. This happens because of the regular increase in molecular mass of the alkanes in the homologous series. Interestingly, the melting points of alkanes having an even number of carbons in the molecule increase differently from the melting points of alkanes having an odd number of carbon atoms. Similarly to the boiling points,
Consider the isomers of pentane. There are actually two things we can conclude from this table. First, the straight chain alkane will have a higher boiling point compared to its branch chain alkanes. Secondly, with increased branching, the boiling point decreases. Increased branching in an alkane molecule gives it a more spherical shape. This reduces the surface area for molecular interaction between the alkane molecules. The extent of weak intermolecular van der Waals forces of attraction decreases, which leads to a lower energy needed to overcome the intermolecular forces of attraction, which is why branch chain alkanes have a lower boiling point compared to the straight chain isomers. The solubility of alkanes is related to its nonpolar nature. This is because the carbon and hydrogen in the alkanes have almost the same electronegativity. Therefore, there is no permanent dipole moments on the alkane molecule. As such, alkanes are insoluble in polar solvents like water, but they are soluble in organic solvents like ether and benzene. Why are alkanes soluble in organic solvents? To answer this, we need to use what we have learned during our chem bonding. The weak van der Waals forces of attraction between the alkane molecules are compatible to the weak van der Waals forces of attraction between the nonpolar solvent molecules. Therefore, organic solvents can penetrate between the alkane molecules and solvate it via solvation. In Chapter 5, we are going to study a few reactions that the alkanes can undergo, paying particular attention to free radical substitution. Due to the non-polar nature of alkanes, they are generally unreactive towards polar or ionic reagents like acids, alkalis, or oxidizing agents. However, they can react to non-polar substances like your oxygen, chlorine, and bromine gas. As can be seen from the table, alkanes has no reaction with sodium hydroxide, concentrated sulfuric acid, and also acidified potassium permanganate. The combustion of alkane is a highly exothermic reaction. This makes alkane an important fuel which we can use in our daily life. Alkanes can undergo two types of combustion: complete combustion and incomplete combustion. In the complete combustion of alkane, we will get water and carbon dioxide as products. In the incomplete combustion of alkane, we will get water and carbon monoxide as the product. Last but not least, alkane can undergo free radical substitution reaction. For alkane, free radical substitution involves introducing one or more halogen atoms into the molecule, and hence is also known as halogenation. For example, methane can react with chlorine gas to give CH3Cl and HCl. Note that the reactivity of a halogen decreases down a group from fluorine to iodine. As the name free radical substitution implies, free radicals are required for the reaction. So, how are free radicals formed? Free radicals are formed by homolytic fission. Homolytic fission is the breaking of a covalent bond between two atoms such that each atom has an equal share of electron. So, what are exactly free radicals? Free radicals are highly reactive species with an unpaired electron formed by homolytic fission. Free radical substitution occurs in three steps: initiation, propagation, and termination. Understand more about free radical substitution reaction from a video clip on the next slide.
When methane and chlorine gas are mixed in the dark, they do not react. However, when this mixture is exposed to ultraviolet radiation, a violent reaction starts. This reaction, called free radical substitution, proceeds via three successive steps called initiation, propagation, and termination. When methane and chlorine gas are mixed in the dark, they do not react. However, when this mixture is exposed to ultraviolet radiation, a violent reaction starts. This reaction, called free radical substitution, proceeds via three successive steps called initiation, propagation, and termination. When methane and chlorine gas are mixed in the dark, they do not react. However, when this mixture is exposed to ultraviolet radiation, a violent reaction.
The free radical substitution reaction comprises of a three-step mechanism. The first step is called initiation. This is the step where free radicals are formed. To describe this mechanism, we will take the example of methane reacting with chlorine gas. During initiation, chlorine gas is supplied with energy in the form of UV light and split into free radicals via homolytic fission. Initiation cannot be carried out in a dark room or at room temperature. When writing the equation, notice that the chlorine radical is represented as chlorine with a fully shaded dot. The second step of the free radical substitution is propagation. This step continues to generate free radicals. What happens in the propagation step is that the chlorine radical formed in the initiation step will abstract one of the hydrogen atom of an alkane, which is methane in this example, to form a metal radical and HCl. This metal radical will react with another molecule of chlorine to generate another chlorine radical. This chlorine radical reacts with another molecule, and this process goes on as a chain reaction. A mono-substituted product of methane, CH3Cl, is formed. The next step of the free radical substitution after propagation is termination. Please pay attention to the video clip in the next slide and understand how termination step is carried out.
Propagation stops when any two radicals collide and combine to give a molecule. This step, named termination, occurs in three possible ways: producing chlorine, chloromethane, or ethane molecules. During this step, all the free radicals are consumed, so the reaction stops. Propagation stops when any two radicals collide and combine to give a molecule. This step, named termination, occurs in three possible ways: producing chlorine, chloromethane, or ethane molecules.
During the propagation step, monosubstituted methane molecule is formed. However, the propagation can be extended. If there is excess chlorine during the reaction, further substitution can occur during the propagation step to give us a disubstituted product CH2Cl2 and a tri-substituted product CHCl3. A fully substituted product of CCl4 can also be formed. In the presence of excess alkane, most of the product formed will consist of the monosubstituted product CH3Cl. However, in excess chlorine, the major product formed is the tetrasubstituted CCl4. Please attempt the self-practice question on free radical substitution. You can click on the answer button to check your answer once you have finished. You can now review the whole free radical substitution mechanism by watching this animation. Please follow the instructions at the bottom of the screen to reach this animation. You have moved to the second checkpoint of the entire e-learning module. Answer these questions and see how well you have understood chapters 4 and 5.